I'm honored to have this opportunity to come to Sinica to share my past experiences and struggles of putting the latest computer vision and deep learning algorithms to work. And a brief introduction of myself, thanks to Dr. Chen. I've been at a few different places and did some stuff. And when I did my PhD, I wrote some papers. And these are some of the slides just to share with you of what I did during my PhD research. So we're very lucky nowadays because we really we don't need to have these very annoying pixel-wise labeling in order to train our deep learning algorithms to learn stuff. Whereas when I was still doing my PhD, we need to spend a whole lot of time annotating the ground truth so that we could actually train stuff. So this is a more relevant slide. I was the first student of my PhD advisor, Jason Corso, and now he's at University of Michigan. And we had this grand vision of helping to bridge the gap between the low-level classifications and segmentations with the higher-level semantic understandings. It wasn't quite possible during the past 20, 30 years, if you're familiar with these computer vision research, because of the recognition accuracies and all these different issues. But we thought the time was about right, and we did get quite a good number of grants, up to $5 million US of grants working on this problem. One of the reasons that I was so glad to join Viscovery is that I view it as a continuation of my PhD work, because we're doing exactly the same thing, but we're using it for a very specific application that is making more relevant video advertisements. May not sound like a grand goal, but itself is challenging enough already. I'll talk more about it later. So my year at GE, I did more theoretical stuff about domain adaptations and classifier adaptations, and also worked quite a lot of work on these graphical model stuff and stochastic optimization. And of course, the years at GE and Siemens, they're big medical imaging manufacturers, so I also did 2 papers on these medical imaging problems. So before we start, there's only 1 hour of time, and yesterday I spent more than 4 hours at National Taiwan University of Science and Technology going through these same slides. So we might have to sort of speed up a little bit. The reason that I became so passionate about putting the latest research results into work is because I did see some problems in the current industries. And I've also observed firsthand that even in the United States, for 100-old corporations, you need to constantly reinvent yourself every 10 to 20 years. Otherwise, you would just fall into irrelevance and just die gradually. So, and it was quite astonishing to me that even the 100 years old, the average shelf life of companies on the S&P 500 index is only 20 years. So this is one of our pride of Taiwan, Foxconn, but it's also a sad story, at least until this part, at the end of the graph. When it first began its business, its profit margin was higher than 25%. But as more competitors gained the know-how of doing the exact same things that they're doing, its profit margins gradually diminished. So what do 100-year-old corporations do, like GE? So GE is the company founded by Thomas Edison, and they made light bulbs in the beginning. And this is their first light bulb factory in upstate New York, in Schenectady, New York. But it's still churning out stuff nowadays. But it's no longer making light bulbs, of course. So what exactly happened? So Thomas Edison kept on inventing stuff, and they made light bulbs for 10, 20 years, made good money out of it. But then radios came out, and the same factory started making radios, made good money on it, and then televisions. And that particular factory, it stopped at making nuclear power plant components, the steam turbines for nuclear power plants. And because the United States government don't want anyone else to do these kind of stuff, so they could just keep on doing nuclear power plant related components for a good time. And being at GE, we also like to look a lot into IBM's plate. GE is always trying to go after IBM's lunch, whereas IBM is always trying to get into GE's territory. So when I was a kid, when I was younger, in 1995, I was very surprised at why would IBM sell its personal computer business. I thought this company is going down the drains. I didn't realize that they are just giving up things that don't make that much profit anymore. If it's less than 5% profit margin, they just sell it completely for a good price. So they actually branched into these integrated solution businesses, and they made good money making like the whole supermarket cashier systems. 90% of the supermarket systems in the United States are made by IBM, and also most of the major cities in Europe, their tow systems, from the license plate recognitions to the whole database to the website, it's all maintained and provided by IBM. So they made some good monies out of it, and I didn't really realize what they were doing with Deep Blue when they started playing chess with it, right? Did anyone of you knew what they were up to? So actually they had the vision, and they thought that they would have to reinvent themselves again in 10, 20 years. And now the first self-driving bus, not car, that's running in the United States, in Washington, D.C., it was actually made by IBM. Not to praise them, but they are at least better examples of companies that are always aware of their vulnerability and always trying to reinvent themselves to survive. So a little bit more about these sadder stories. You can see in this nice chart here that the semiconductor business, many of them spend 20 to 30% of their revenue on R&D. And I love Qualcomm CEO's famous quote. I also have a good number of friends at Qualcomm when they first started their computer vision business. Instead of doing OpenCV, they did one that is tailored for mobile processors called FastCV. It didn't completely turn out to be a great story, but their CEO had this mentality that if I throw 100 ideas on the wall, and if one sticks, even if it's not directly applicable in 1 year or two, it might take 3-5 years for it to mature, but they're fine with it. It's very different mindset from what we have here in Taiwan. So even for our beloved company NVIDIA, it actually reinvented itself twice during its 20 years of existence. So what happened? I suppose there are some of you here that are old enough to have installed Voodoo 3D graphics processors in your computers to play games back in 1997. And NVIDIA came into dominance when they introduced their 2D plus 3D processors, the TNT series. And they had a very good market share, 44%. But eventually, Intel started to sell their crappy 3D accelerators, and they got almost the whole market. And the gaming population isn't really that big to begin with. So NVIDIA really ran into some roadblocks in around 2005, 2008. So, of course, nowadays when Huang Renxun goes towards the world and gives these speeches, he likes to say, yeah, we saw deep learning was coming. We made deep learning specific chips starting in 2008 already. But they did struggle a bit, and they tried to find new directions. So they actually tried hard branching into the mobile computing business. And given the popularity of Android devices, you might think that they did pretty well. But actually, they've always been number 4 in the mobile chipset market because they're Tegra processors, although they're powerful 3D. But they don't really, they consume too much power. So what's happened? So nowadays it's clear because this is what we see during typical NVIDIA presentations. He talks a full hour or two all about deep learning. And but so in 2008, what they tried doing is they tried to introduce these general purpose GPUs. And they just happened to make these kind of functionalities at the right time, and it was a perfect fit for deep learning applications. So long story short, let's get into the important parts of today's talk. So just something to think about. And this is something that I really had some very deep thoughts, especially during my years when I was still aboard before I came back to join Viscovery. And I'm really glad to see all these startups coming up in Taiwan. But we're still at a very early stage compared to other places with great startup cultures like Silicon Valley. So on the other end of the spectrum, so on the big corporate side, they try to constantly reinvent themselves. They have plenty of resources, but they also have their bureaucracies. So on the complete opposite side, there are these startups. They don't have that much resources, and it might be young kids with some dumb ideas that are trying to make a name for themselves or trying to do things they care about. An important definition. Many Taiwanese people don't get it, but startup must be an organization of some sorts that is in search for a new, repeatable, and scalable business model. So if you just open up a coffee shop at the corner of your streets, it's not a coffee shop, or Wenchuang, it is not. Because even if you succeed, it cannot be scaled greatly. When you open another coffee shop, it won't be, because your competitive advantage or your entry barrier is because you established a good relationship with your existing customer in that area. But if you move to a new area, you have to start all over again, then that is not considered a growable business model. So I'm going to skip over most of the startup slides because that's not what today's talk is about. And this is a very interesting chart that I would really like to share with you and to think about. We know that in order to succeed as a new player in town, say there's already 10 face recognition companies out there or 30 smart surveillance companies out there, and you are number 31. How are you going to stand out? How are you going to survive? So when you're positioning yourself, there's two risks for startups that you need to consider seriously. One is the technical risk. How much uncertainty is there in building your new technology for this particular application? The other is market risk. Is it already a proven need, or is it something that others have never even experienced before and you have to sort of shove it into their mouth? So you could see the grayed out logos here are all the failed startups. And I suppose most of you have never heard of Coda. Any one of you here heard of Coda? No, it's actually the brilliant idea of Warren Buffett. So when he visited China like 10 years ago, he saw some local company, and one of them was BYD. And he thought, okay, these cars are doable. If you could sell us the empty car and we'll just take out your engine and put some batteries into it, we have an electric vehicle for less than 30,000 US dollars. I think it's going to be a hit. So when they did their surveys for market risk, yeah, people would buy a $30,000 electric car. Why not? Even after the government subsidized, it would become only like around closer to $20,000. And the technical risk is low because everything is mature technology. They don't need to start from scratch. But did the customer want to buy them? Turned out that it didn't work out too well. On the other hand of the spectrum is like Tesla, or like when Google first started out. In 1997, when I was making websites, there weren't really that much out there. We just had to register our own website under the sports, community, discussion categories. And I thought Google was crazy back then. Like, why would you need something that crawls the web automatically? But they saw things differently because they saw the number of websites and the internet traffic. It's going to be an exponential growth. So they realized the need. And it's the same position here for Viscovery. Even nowadays, the number of videos on the internet is just growing so fast. And all these video hosting websites, they can't just use their old, inefficient advertisement models forever. Otherwise, they would all go bankrupt, or they would all start to have to charge the viewers some amount of money when you view it. So Um, I'll just quickly go over this as well. Won't go into that much detail. And since I've been doing computer vision, it always amazes me. Anywhere I go, even in Taiwan, people would know what this person is, even though we're not familiar with this historic figure. Yes, Lincoln. That's super amazing because you see it's only like 20 by 15 and people see that this is Lincoln, but how do we do it? Computers are not so fortunate. You only see a 1 above a 0, a 103 on the left of 143. What does it exactly mean? So all these brief histories, I believe many of my friends, like Jia Bing, he shared similar slides and talks before. So Ivy League professor Marvin Vinsky thought, just give me a grad student, 3 months of time, and I'll hook up the camera to the computer and make it see. So this is a photo that is in addition to what Jia Bing had in his slides. So this is the computer that they were using at that time. They only have like 12 inji 射线, I don't know how to say it in English, CRT whatever things, and they shoot out circles or squares or random patterns like that. So it was indeed quite ambitious, and the student, although eventually he became an Ivy League distinguished professor, Gerald Sussman, but he never worked on computer vision ever again. So it's really super challenging. So I'll quickly go through all the struggles that we as a community had to go through. Some filters that we handcrafted early on, and finding straight lines and finding features. And so a sift feature, it's worth a little bit more attention here. So it's one of the fewer things that actually works better in our early days of handcrafting features. And this is the Mars rover, and it automatically found those sift feature points, and it matched it with another view that is very different, but those are matching points. So it does work pretty well for some cases. And in early days of Viscovery, we did use SIFT quite a lot for product matching and recognition. However, with the introduction of the latest deep learning-based features, as it turns out, even for the simplest and a problem that we thought that is solved, these SIFT-based features, they're beaten by the features that are learned by deep learning. And I think Professor Chen's lab here also works on similar problems like this. So, and another thing that's worth a little bit more time here, of course, Gabor filters, is that nowadays when you use deep learning, no matter what you use to learn, whether it's faces or objects or scenes, the bottom layers, they're almost features, like almost always features that look like Gabor features. So I'll also quickly just go through all this, and I think many of you here are also familiar with the slide. Deep learning is powerful because it learns important features from the data that you have. And the previous struggles that we had of not being able to learn the difference between, say, a orange and an apple properly is because we're describing it with the wrong features. Can you imagine that you go to a market and try to tell someone that, okay, I want to buy an apple, tell the difference between an apple and an orange, but I don't have color in my vocabulary. So you'd say, okay, I want something that is slightly smoother on the surface, maybe it has a stem, and maybe there's a small dimple on the side. No matter how hard you try, you might still have a hard time distinguishing some of the apples from oranges. Whereas when you have the right features, just tell them to look at the color. Red is apple, orange is orange, and then your classes are solved. So this is another interesting thing that came out from 2013. So when deep learning first came out, the original champion, the deformable parts models that I skipped over. Back then, researchers were so desperate that we crafted these complicated models to represent complicated objects. For example, cars, where we could only see like 2 to 3 of the wheels at the same time, whereas the rest of the car is hidden. And so we thought it might be that we didn't have a strong enough representation for the object. So we came up with these things. And in the early days of deep learning, when there were only 6 to 7 layers, where it can't really learn that complicated a structure, DPM actually did beat deep learning in a good number of categories. People don't talk about these early day things that much anymore, but that was indeed the case, like bike, car, horse, or person, or motorbikes. So, but deep learning developed quickly, and this is also an old slide. Unfortunately, 2 years ago, deep learning only had some edge doing the above tasks. But nowadays, it's also good at doing joint image segmentation and classification, also very good for MRIs, medical image segmentations, and also it does a better job at license plate recognition. And not to mention that for even the simplest feature matching tasks, the features that are learned by deep learning, they are much more descriptive. I don't know when it's going to revolutionize the traditional fields like biometrics and stuff, but we'll see. So I'll quickly give a overview of the maturing computer vision applications, and later on I'll talk about the ones that are still in progress, and then reflect upon myself, and then finally have some more discussions with you guys to see what we could still do as the top researchers in the academia. Okay, so machine vision, as complicated a task as it might seem, like inspecting the blades of the latest GE turbine engines. You know that the latest 777 and 787, their blades are made of carbon fiber, and they don't just gradually crack. When they crack, they splatter. So it's definitely not a good news. So they need to go in there and regularly inspect those blades to make sure that they are fine. But those tasks turn out to be simple. We could use very traditional image processing methods to find whether there's cracks or whether there's openings, closings, etc. And we are able to do a good job. So Cognex. Cognex was a company that I really liked as well. My former mentor at GE, and he's now the director of the computer vision lab there. He worked at Cognex for many years, and they do machine vision, computer vision at the super rapid speed. Bottles go through the inspection stations 120 frames per second, and then they would take 4 high-speed flashes, and because they knew what the bottle is like, they've had this 3D model already, so they could just rapidly project it onto a plane to reconstruct the label. And then they would match the label using simple algorithms to determine whether the labels have been misplaced. So it might not be that important for beer bottles, but if you are in a biomedicines industry, you definitely don't want your bottles to be printed incorrectly. So it's able to detect things like label damage, wrong label, position, etc. And all these are done with just simple image processing and basic computer vision techniques. So license plate recognition. It's also quite amazing that our early day researchers were able to just do some projections and thresholdings, and then were able to crop out the individual characters. Nowadays, we sort of revisited this problem not too long ago with deep learning methods, and they're not really that much better at cropping out the characters, to be honest, if they're nice and clean like this. Okay? So biometrics, because of the well-defined features that we're looking for, including arches, loops, and whorls. So our handcrafted features managed to work pretty well. And but there's an exception. So if you're still using AdaBoost for face detection, stop doing it, because it's really not that ideal, even though we've been using it for more than 20 years. In our heavy benchmarks inside, in the more challenging situations in videos, they only achieve less than 70% precision and recall when you're trying to pick up the famous celebrities in those videos with lots of lighting and angle changes. So I won't go into too much detail of how we're doing it, because we're doing it like 10 times faster than AdaBoost now, and also like closer to 90% precision and recall. But this is something to rethink about. Something that we thought is solved already, but actually turned out to be not so solved. But it's not too hard to perceive and understand because if you think about it, they're just using these super simple hard features for the detection. And even though face verification is considered sort of solved, but actually it's only solved for certain cases. And for label faces in the wild, everybody is getting 99%, so it's no big deal for one-to-one verification. But like the latest megafaces database, even the top performing methods, they drop to 50% to 70% accuracy. So any one of you know what this is about? So this is also a technique that is done without deep learning. It's National Football League, NFL, and the broadcasters, they started drawing these 10-yard line, the first down lines in real time, without any computer vision, without any deep learning help. So how did they do it? So every season, they go to all the potential broadcast camera positions and take nice photos and build a model of the stadium. And then whenever they're actually broadcasting in season, they would then take this image and subtract the background, which is already maintained. And then they would figure out what are the foregrounds, and then they would draw these lines on top of it, and then put the players split back. So nowadays, still a huge amount of American population don't understand how they did it. And they thought NFL workers work really hard and efficient. Like every time the camera turns away and then turns back, boom, there comes the line. Okay? So all these 3D reconstructions, the structure from X, many of them, they still use SIFT, but the latest research, it's also showing that we have better ways of matching the features. But this is one area where SIFT is still holding up pretty well because it's not just used for all these structure from X applications, but also there's more examples to follow in the next session. So with image panoramas, with those SIFT features, we're able to tell what relative positions these photos are taken. And then afterwards, it comes the challenging problem of putting them all together. And I'm a little ashamed, but also not too ashamed to tell you that this is what I spent most of my time during my graduate school career doing, Markov random fields. You come up with these very high-dimensional, complicated graphical models, and all you're trying to do is to make sure that the things, this is one of the applications, of course, they're nicely stitched together. So you could see that the algorithm from the 1980s, it's, yeah, you're missing a torso, missing a leg, missing a head. And with the introduction of belief propagation, you're able to do a better job, but still you're missing some legs. And graph cuts sort of just solved it for all, once and for all. And you would finally be able to determine if you are 30% likely to take this pixel from this image, 40% from that image, and 20% from this image. How are you going to put it all together to form an image that finally makes sense? So photosynthesis. This is also a problem that fascinated me a lot. And I also spent quite a good amount of time on it. Even for something as simple as this, you crop out one thing, crop out two things, and put them together. In order to make it look nice and natural, you have to go through all this, build a complicated graphical model and solve the energy minimization problem. And finally, you get something that is like, okay, now I know that at these boundary regions, this is supposed to take 30% foreground, 70% background. And then when you put things together, you would finally get a nice looking synthesized photo on the left. But now looking back, I think of it as a unwise research topic because all this hard work, and it turns out to just be a small function that most of the people probably wouldn't even use in Adobe Photoshop in their whole life. So if Adobe Photoshop sells for $100 a piece, how are you going to expect Adobe to pay you more than 50 cents or 10 cents for every license that you get? So, and of course, with the mature of image, scene classification, and object detection, it really enabled us to do a lot of things. And I've got some interesting photos from these earlier days of these self-driving car challenges. The DARPA Grand Challenge in 2005, Stanley drove through the desert at 3 miles per hour, which is like 5 kilometers per hour, and won the competition with all the sensors on top and surrounding it. So this is a diagram of all the sensors and how they're connected for Stanley. And later on in 2007, they tried to make the cars drive through an urban area. Luckily, no one was hurt or killed during this exercise. The winner from CMU, which is where Frank is from, won the competition with a lot of sensors still, but they did it at 13 miles per hour through the city. But it did advance quite rapidly, and you can see that a whole lot of these sensors are gradually replaced by vision-based components. And this is the vehicle that CMU ushered a US congressman to the airport, drove on the highway at 70 miles per hour for 33 miles, and they made it to the airport in one piece. Okay, so Google's self-driving car, later on they've hit everything, all the computing powers and most of the sensors except for the one on top. That is not a computer vision component. It is a very expensive LiDAR component, typically with 12 or more LiDAR sensors that it just constantly circles so that it could get a detailed view of all the potential obstacles that is surrounding it. But so this is NVIDIA's self-driving car, and you can see the driver's 2 hands on it. If you've watched any of the NVIDIA's presentations recently, you would have realized. So it's no sensors at all, just stereo camera, and it doesn't even, they don't even program it. They just let it take all these inputs and then learn how to drive in a closed course to begin with, and then it would gradually learn how to avoid the obstacles and then drive by itself. So how did they do it? For those of you that had participated in earlier day self-driving research, you might recall that we had databases like CamVid, the Cambridge Video Driving Databases, and many others, where we try to recognize all the obstacles in the video. But that's not how NVIDIA does it. So this is a point of view video from a driver in Germany that's doing 200 miles per hour, 300 kilometers per hour on their Autobahn. And you can see at this speed, if you try to focus on all the obstacles, they just go by so fast. And if you focus on the obstacles, you're more likely to crash into them instead of drive around them safely. So that's the trick. NVIDIA's self-driving system nowadays, they don't learn any obstacles at all. It only tries to learn areas that is drivable, the green area. And it's actually a much more manageable task, and they've indeed made pretty good progress on this problem. Okay? So here's some of the up-and-coming, still maturing computer vision applications, including a structure from X-Type called Floor. It's a startup in New York City. They go in, take a camera, take a video of the upscale apartment, and do a 3D reconstruction with the help of some 3D artists, so that the super rich billionaires, they don't need to get out of their homes to view new apartments to buy. And also, Pix4D, they use the same structure for motion algorithms, but use it on the drone to reconstruct nice 3D models for important landmarks. So object recognition. I like Blue River technology a lot. Nowadays, people want to eat organic, healthy food, no pesticides, everything. But if you want to grow things organically, you can't just hire a lot of low-cost laborers to pull out all the weeds. So Blue River technology, their camera, they recognize carrots from weeds, or any product or any produce that you're planting from weeds. And if it's a weed, they would move a hose close to the weed and inject hot water into it. So I really like the idea. And if I were in the States, I would really like to help them because I think it's just something super fun. Okay, so I also have some friends that work at Magic Leap. They are another up and coming application, but this is a little crazy because augmented reality nowadays you need to wear these heavy goggles, and what Magic Leap tries to do is they try to shoot laser directly into your retina so that you can no longer tell the things that you're seeing as real or unreal or synthesized. And because they're founders, one of their technical important guys, Gary Bratsky, the father of OpenCV, so they managed to get a whole lot of funding at the very beginning. And they're releasing their products now after some of the turbulences that is usually expected in a startup. So, of course, so I would like to sort of bring the story back to help you guys, help the audience think. We've always got all these different awesome things going on in our research labs, but what are the ones that I should focus on if I really want to make a difference in connecting the industry or even revolutionizing the industry? So I'm RSV, a startup that provides not just face recognition, but like the gender, age, emotion, attention, all these things. But with the great number of face recognition companies out there that have already done, like hook up their systems with one of their existing providers with their APIs, you would take a much longer time to persuade them to switch. B2B is very different from B2C because when you're doing B2B, typically your two systems need to be integrated to a certain degree. And in those cases, it's going to be harder for a newcomer to persuade your customer to switch because they have their whole ecosystem built around that thing already. And also some of the things that we in Taiwan talk more about, including like Internet of Things, retail insights, or like, I'll skip over this slide, including smart surveillance. But like in Taiwan alone, there's more than 30 smart surveillance companies, and there's more coming. I know a good number of friends that are still starting up smart surveillance companies. And not to mention that the technology is extremely challenging in the sense that when you get things right 99.99% correct, you would still make one mistake every 10,000 times, and people would be angry at you. And if you get it up to 99.9999, you would still be incorrect one time out of 1 million times, and people would still be mad at you. So, and that's why a lot of cases, they are able to get the contract, they execute the project, but they're not able to close the project because the customers would say, no, you haven't completely automated this process. And which is also something very important to think about. When you only have a system that is only correct 70% of the time, how are you going to make it work in the real world to make money, of course, but also to help a industry or existing application? So here's a little story about my past attempts at making the latest computer vision algorithms work. A few startups that I worked after I left GE. So Tandem, it was funded by the Dolby family, the family that did Dolby Surround Sound, Dolby Denoising, Dolby Digital. So they shared the same vision that shadows and lighting issues are just a source of noise in computer vision problems. And if we could actually remove or at least alleviate the problems of shadows, then the problem might be half solved already. So it took us a long time, and this is one of our first products, Lightbrush. I also worked on it. So as long as we know that these are the same textures, and this is a bright point, and this is a dark point, we call it the lit-dark pair. And we're able to compute, project them onto our proprietary color space and find out how exactly this particular light source is from and how it's causing these lighting and shadow issues. This is a real-time demo that is recorded running our system. You can see that we're actually able to get the textures and the lightings separated pretty nicely. And with things like this, you could do silly stuff, of course. You could put things on and then just move them around, and after you put the shadows back, they would still look realistic. And this is just one of the many applications that we could use it on. But like, this is, when I'm looking back, Tangent is the perfect counter example of a lean startup. They did not do prototyping. Any one of you here know what prototyping is? Yeah, so even before you do a prototype, even before you start writing a single line of code, you try to validate whether this business is viable. So not just startups do that, but also IBM did that. In 1970s, IBM wanted to see if a computer that understands spoken language would actually have an appeal to the market. So they built a wooden crate, put 2 of their engineers into there with a computer and a keyboard, and pushed it to the showrooms. And when the customer came and spoke to the crate, 2 guys in there would start typing, "Hey, how are you? I'm good," and stuff like that. And so they validated that this is a good business idea before even writing a single line of code. And it's super important because as programmers ourselves, we sometimes get too tied into the stuff that we create. And sometimes when people finally come to you and say like, "Hey, that app is crap," you go to Adobe and you can't even sell it for $1 per license. That's exactly what happened. So, but $1 per license is not even enough to overcome our R&D efforts. But it was super awesome stuff. So because Adobe didn't want to buy it, so this is an expert, Bob from Adobe, demonstrating how you could remove shadows in Adobe Photoshop. So this video lasts for 9 minutes. I'm going to cut short, of course, but that's what you still have in Photoshop nowadays. Okay, so because after we developed all these algorithms, we realized like, oh shoot, it was also my first startup, so I knew nothing about what is the right way to do things back then. So like, okay, we got to find a way to sell all the things that we have developed. So we tried to crack into the advanced driver assistance market. So you can see that this green light here, it's the lane departure warning system on my Honda. And you can see that when you're going in and out of shadows, it sometimes beeps, sometimes it does not, because the shadow is greatly confusing its algorithm. So we thought, yeah, if we pre-process all the shadows first, and then if we just then try to detect the lanes, we would be able to pick them up all the time. So this is another example, counter example of lean startup, because Mobileye, they completely refused to use this thing because it required quite a lot more computing power than what they already have on their chip. So we actually had to get additional money to make it into a hardware-based system for the driving applications. And this doesn't work for all cases. The reason that I had that big yellow rectangle and that big blue rectangle is because it only works if we already know where the lit dark pair is. And the reason that we have to go after specific applications is because we could train a classifier to automatically place the lit dark pairs. Okay? So the shadow problem, it's still not solved, but at least we had a workaround around the first, some parts of it. So this is my colleague and demonstrating like it could also be used to detect whether the driver is drowsy. But these type of systems that are selling only for $20, $30 a piece to the OEMs and the price that we've put into development, it just doesn't make sense to them. So also did some structure for motion things after I moved to Houston, as well as satellite imaging stuff. So there's plenty of energy companies in Houston, and they would want a more efficient way to help them lay the pipelines, or even for alternative energy providers want to help people estimate how much solar energy they could generate from the shape of their roof. When we were still pitching around working on a prototype, Google came up with a completely free version in just 3 months. So, so because anytime when you think that you have a great idea, or you realize that you talk to some business partners, potential business partners, they have this need, you're not the only one with this idea, nor are you the only one that they've talked to. And for young folks that we are able to pull all-nighters right before deadlines, we think that, yeah, we work fast, we are a great team. But if you're looking at actually making things that works in companies or startups, you will be looking at a sprint of 3 months, 6 months, or 1 year. And it's not just about pulling all-nighters before the deadline. It's about careful planning and precise execution. And that's something that many of the younger folks don't really have the experience about. Even I'm still learning how to plan better and execute better. So, and I can't really talk too much about Nerve. Nerve does quite a bit of intelligence and defense applications. And the thing that I took out of Nerve was that they had a huge amount of videos, and they had to do these searches or matches at insanely fast speed, up to 100,000 frames per second, using simpler algorithms, of course. But many of the optimization skills that I learned there turned out to be greatly beneficial for my current job. So, Viscovery. Viscovery, I was contacted by Viscovery a little bit over 1 year ago, and because Viscovery started out in Taiwan. Our founder, he did many of these projects, didn't really become a startup until 2013. And then the founder decided to use the recognition capabilities that we have accumulated to help many of these retailers to recognize products. And put these recognition capabilities into their apps. So the hot thing back then was called O2O. And nobody nowadays talk about O2O because it's a dead concept. People realize that you can't make money out of O2O. So what happens is that, okay, you spend a lot of money developing the recognition capabilities, you put it into the app, you persuade the user to install the app, take out their phone, take a photo of the product, and then recognize the photo 70% of the time. And hopefully they would be interested and then click on the comparison and compare the prices and finally decide to buy a $100 product, and you probably get like $0.1 out of it. So it's good to accumulate a good number of customer list, but it's not really that good for making money. And you really have to make money to survive as a company. So when our founder went to China to try to expand the market in 2014, we are deeply in red. He owed quite a lot of money. So luckily, one of the investors that came to us, SoftBank, they saw another opportunity in China. That is because they have tens, 20s of video streaming websites, Youku, Sohu, Baofeng, blah, 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 whole lot. And they're not making that good of money because they're splitting the same pie that YouTube eats all by itself. And the advertisers, they're not happy with the effectiveness of these advertisements. So in 2014, Tengxun actually hired 2,000 human laborers to manually annotate what is in videos so that they could make more relevant advertisements. And don't laugh at this. Actually, Google generates 90% of its revenues from advertisements. Google is an advertisement company, and actually advertisement activities, it's so important to human societies, all the economical activities. It's one of the cornerstones. So, but it turned out to be a much more challenging problem than we realized. When you put a car ad in the video, it's not just about detecting the occurrence of a Mercedes-Benz. If it crashes, or if the man and woman is fighting on the car, or even if it's Zhou and he's dancing some silly dances, you probably don't want to put something that he's, a spokesman for at that particular moment. So it's not just about detecting the objects, but also the faces, the scene, the text, audio, motion, and objects, they're all relevant. So for example, Nike, they don't really care what things are happening in the video. As long as there's someone running or jogging and it's slightly positive, then they would want to put their shoe advertisement on it. And for example, Budweiser, they don't really care what objects appear in there. As long as people seem to be having a good time, even if it's in a nightclub, completely dark, just some flashing lights and music playing, they want to put their advertisement there. So it turned out to be a much bigger problem than we initially anticipated, and then what SoftBank investors initially anticipated. So we had to start developing all these different technologies, and that was the point that I joined Viscovery because, and later on I persuaded a whole lot of like-minded people to join. So it's not just me that came back from America, but there's also, we have researchers that just came back from Columbia and also Michigan and also Max Planck Institute in Germany and also folks that study abroad in Australia and other places and UK. So we saw that now we don't really want to do IoT. There's too much problems, and we agree, we share the same vision that this is probably something that's worth pushing, and because of this unique situation in the Chinese market, we could, and we, Viscovery moved first. We have the first mover's advantage. So we might be able to do something and help establish an industry of computer vision and machine learning based things. So if you're interested in more demos of our product, I'm not here to advertise Viscovery. I'll just quickly skip over. So nowadays, what we're getting is that if we have a video, it runs through our analytics system. We have face, object seen, and all these things recognized. We provide an interface so that originally, if you need to spend 60 minutes to slowly go through the video to determine, okay, I'm going to put a car ad here, we hope that all this recognition would help greatly speed up the decision speed. You only spend 1-2 minutes, quickly click through the items that we've recognized, and then it'll fast forward to that moment, and you could play the video for like 5 seconds or 10 to determine that, okay, if it's a nice place to put the ad, we'll do so. So hopefully you'll be able to reduce the human effort needed to like 10 times or faster. But there's a great deal of problems that we encountered even during the past year. So when I talk to people and talk about all the things that we've been through in the past year, and people would be shocked to learn that, what, you guys only did this for like a year? You've only been there for a little bit more than a year. So when I ask researchers, if you have a recognition algorithm that completes a task, runs it on the most beefiest GPUs, and if you complete face, object, and scene recognition at the cost of only 1 cent per image, do you think it's fast enough for this problem? You might think so, but actually, if you think about it, there's more than tens of thousands of frames in a video, and in order to get these more precise information, you can't just run it on every frame and eventually costing the customer more than $100 per video. That's close to human labor cost. So also the number of categories, all the examples that I've mentioned, all those different things that we needed to recognize that we didn't realize was needed beforehand, and the recognition accuracy. If you only have a system that is overall only 70% accurate, how could you actually make it work? Because if it says that there's a Zhou Jielun, and 7 times out of 10 times it's correct, but 3 times it's incorrect, that would translate to much more human effort. And also, what if it's missing out important Zhou Jielun instances? So, and also the recognition speed. You can't just take 1 cent times 10,000 frames and charge the customer $100, 200, or 300. Nobody knows what Viscovery is, and why would you give 1,000 videos to Viscovery and let them charge you an arm and a leg to analyze this? So that's one of the points that I've been pushing really hard at Viscovery during the past year. Last September, shortly after I joined, our system runs all those 3 recognitions at only about $20 US per 1 hour video. And in June this year, it's down to only $2 US per 1 hour long video. And this is not done by some parallelization tricks, because if you parallelize, you have to open up more machines, and they're all going to cost you. So you have to optimize from a mathematics level. Go back into every equation and find a acceptable approximate solution if needed, and then also from the algorithm point of view, massively parallelizing everything. So we're pushing for, hopefully by the end of the year, we'd be able to reach a cost of less than 0.5 US dollar for analyzing a 1 hour long video. And with the cost list though, that's really an edge that we're building, because any newcomer like VSense in Singapore, the mastermind behind it is a National University of Singapore's Chen. And they're still happily doing single image based product recognition. Don't tell them about all these roadblocks beforehand that they might bump into. So it really took us quite a lot of effort and a few $1 million of R&D effort to get to the point where we are nowadays. And also, when your single image takes 15, 20, or 30 seconds to recognize, you would design your system architecture in a very different way compared to a system that would finish a single hour long of video in less than a few minutes. And so we're overhauling our overall system architecture right now, because we've managed to speed up our recognition cores so much that most of the time it's just idling, waiting for the network communications to finish. So, business model. Before we were able to push the envelope this far, we really had to beg the customers to sign the contract, so we finally have the money to run some analytics on 100 or 1,000 videos. And they might not always be happy with it, because sometimes when there's a very popular video, people might be clicking it like crazy and it would have a 1,000 time return, whereas most of the other videos where nothing interesting is happening, people might just be clicking at it at a leisurely pace and probably only see a 1-2% increase, even if you do content relevant advertisement. So you really need to get the volume up in order to see the economy of scale. And fortunately now we can afford to do this. Now we're just putting all our machines with K80s, Titan X, and latest GTX 1080. We almost bought the latest DGX1, but our engineers panicked at the last moment and realizing that we only have 8 physical GPUs left to use, and not all the other GPUs that we have at hand, and they don't want to Dockerize all their development efforts and share the time and potentially crashing each other's tasks. So, but the business model, it's really something to think about. So, but I'll just skip over Viscovery's edge. I've talked too much about Viscovery, and life is not all rosy. People sort of romanticize life at startups, but you have to make things work with little to no resources. I had to personally go out there and come here to recruit. Welcome, please join Viscovery. And you have to make things work regardless. There is not a no impossible word in our dictionary. So let's talk about these 4 folks. What can we do? What can Taiwan's academia do to help bridge the gap? You guys all know who they are, right? So Yana Kuhn, he's now with Facebook. Geoffrey Hinton, he's bought by Google already. And Yoshua Bengio, he's always been working closely with IBM. And of course, Wenda, he's with Baidu. And however, we don't have companies with this big of a name in Taiwan, and they don't really value researchers that much and give us that much power and money and freedom. So, and let's take a step back and take a look at what a healthy cycle should be. A healthy cycle would be the general public trusting the academia, providing abundant good students, and then the academia would be producing well-trained graduates to the industry, and in return, the industry is able to keep up good profit margins and provide improved living standards for the general public. So the general public would give reputation and policy supports, and then industries are more likely to give grants and collaborations instead of everybody waiting for 科技部 to give them the money. And then the academia, it would be able to provide opportunity to the general public. You come here and learn and train, and then you'll be able to make a better living. So And of course, many of us have different views. Like Sun also a good friend of mine at Tsinghua, he thinks that the key is to have a very open AI society. But from an industry point of view, from an applied research point of view, I think we are the problem, industry, because we don't have the computer vision or deep learning industry in Taiwan that is as big or as open-minded as those that are overseas. So what happens is that, of course, we're not giving grants to the academia, and because of the lack of this collaboration, so academic researchers just keep on working on stuff that they think is important, but have little direct application to the latest cutting-edge industrial needs. So unemployable graduates, and because the industry itself fails to reinvent itself, so it provides stagnant wages to the public, and the academia would be viewed as providing useless education. So I'm greatly saddened by the 大学无用论 nowadays going on in Taiwan. And in return, so the general public would not provide supportive policies, and they are less likely to go to college right after they finish high school, which is happening in Taiwan right now. So, being from the industry perspective, I think we are the problem, and we really need to get our acts together and make sure that we survive. And in this process, there's lots of challenges, and that's why we really have a different mindset. We really appreciate and want deep collaboration with the academia, because the problem that we're working on is super hard. And many of the activities, of course, it benefits the company a little bit, but also we want to make sure that the academia benefits even greater at the same time. So where should we start? Where should I start? And probably, let me go to this first. So the Goldilocks zone of innovation is right here. Business relevance, academic relevance. In a larger organization, you have plentiful resources, but have a more hierarchical organization. In startups, you have much more freedom, but you are lacking resources. So traditional corporations talking innovation, they're probably at the upper right spectrum. And corporate research, like GE corporate research, they are so closely tied to their business needs that you don't really expect anything greatly innovative to come out of it, but they're always going to be relevant to their business needs. And down here, it's startups struggling to survive, and academic spin-off, they're probably closer to this place. An interesting thing here is Microsoft Research. They've been around for 20 years. They've got great reputation in the academia, but they haven't really managed to make that much business relevance. So a great analogy that I always like to make. The reason that I insist on being in startups instead of being in big corporations' research labs is, one of the reasons is because I've been to Siemens corporate research and been to GE Global Research and saw it's a great place to retire. Don't get me wrong. I would really like to retire there. But like, in order to make things happen, and say you have great ability to present your ideas, you have a 90% probability of success. You talk to your manager, okay, now the probability is 90%. You talk to your manager's manager, they also buy in. Before I reach the CEO, which is about like 10, 15 levels away, the probability already diminishes to less than 5% or 3%, okay? But for startups, even you have the dumbest idea in the world, and only 1 out of 100 would think that, okay, I'll give you a try, I'll help you, I'll fund you a little bit. But you talk to every investor, and if you talk to enough of them, there is eventually going to be one investor that would think that, okay, I think that's a great idea, I'll invest some money into you. So that's the great difference. So it's ironic, but also sad, and which is why that the successful spin-offs from, or the corporations that manage to reinvent themselves at the right time is limited. So here are a few examples that they've got it right, even in big companies like Amazon. So anybody here know that the Amazon Web Services, it was actually the idea of a entry-level engineer and saw all those machine idling. So he went to talk to his boss, and they thought that it was a good idea. So I don't agree with all the corporate cultures that is done at Amazon, including they want to save any penny, but at least they had a pretty direct communication with the CEO. So the manager and the engineer, they went to talk to Steve Bezos, and Bezos thought that, okay, we'll give it a try. So he gave great support, and then it became the most profitable organization in Amazon. And it's the biggest of all, much bigger than everything else combined. And also same case for Gmail. Google has always been allowing its engineers to spend 20% of their time doing random stuff, and many good things have happened along the way, including Gmail. And Microsoft, even though it's the counterexample, they did realize that Microsoft Research can't function the way that it did during the past 20 years. So starting from around 2007, this is Jamie Shotton, one of my idols when I was still in PhD. He did some very good work in Markov random fields. He was at Microsoft Research, Cambridge, London. So eventually, all their researchers went in to make the Connect product happen. And even though the business side, people might question, like, do we really need Connect and stuff like that? But at least it's one of the most successful spin-offs or collaborations between Microsoft Research and its business units. So I don't really have an answer for you in where we should stay in this complicated diagram. The startups that I know of, at least Viscovery, now with our latest round of funding, we want to make sure that we don't have that little of a resource. We want to share as many resource and freedom as possible, whereas still avoiding all the bureaucracies in big companies. And we might be tilted more towards the business relevant side, but if you actually love advertisements, like our CEO and as the researchers that have joined after me, it would be something to consider. Whereas like Sense Time by Tang Xiaou, Wang Xiaogang at Xianggang Zhongwen Daxue, they're more towards the academic relevance side. And they've got plenty of funding. They still have a high degree of freedom in their organization, but they don't go that deep into satisfying a particular business need. And whenever they need to go anywhere deeper, they would spin it off as a subsidiary company. And there's no right place to be, but it's just something to think about in this chart. So that's it for today's talk.